Hello, and welcome to this video in the series on integrated pest management, focusing on disease control in cereals. As I mentioned in the introduction to the series, IPM is a huge topic, and it sits within the wider context of integrated farm management and integrated crop management. And if you'd like further information on that wider context, I'd refer you to the guidance produced by LEAF, Linking Environment and Farming. In this episode, we're going to get to the core of IPM, which is about how to combine or integrate control methods. And particularly, we're going to look at two aspects: how to select control methods and how effective are they likely to be when we combine them. So let's take a closer look. In this video on integrated pest management, we're going to look at the question how to combine control methods in IPM. And combining control methods is really the essence of integrated pest management, and we can think about it through the sort of broadly accepted 8 principles of IPM. So the idea of picking control methods for prevention and suppression, monitoring crops for pests and diseases and weeds, making informed decisions about treatments, the preference for using non-chemical methods. If we are using pesticides, to take care of the selection of those pesticides to minimise non-target effects, and to, where possible, reduce pesticide inputs. And in the way we use the pesticides, to take account of resistance management, and then afterwards to evaluate how successful we've been. And if we just take a look at how those 8 principles look in practice, what it boils down to is, on the left, we're aware of a disease threat, or typically several disease threats. We're picking some combination of rotation, cultivation, the genetics of the variety, agronomy, perhaps biological control if that's available, to ameliorate that threat, and then making an assessment of whether there's a need for a pesticide treatment to back up those non-chemical methods. And if we get those decisions right, we obtain effective control. And then we have the task of evaluating, well, which of those control methods actually worked and did the business? Would less impact from less input still have provided effective control? And what were the effects of those control methods targeted at one pest on other pests? And those effects could be positive or negative. There could be trade-offs. So behind all this, there's a set of decisions about trying to identify effective control methods which minimize those trade-offs. So to help with those decisions, back in 2021, we produced this review for AHDB, in this case, in this particular review, for the major arable crops. And that review is available online. In that review, we looked at over 500 sources of evidence and reviewed and interpreted them for the UK about how effective and practical they're likely to be. For those 4 crops, we found evidence on 40 IPM control measures against 80 weeds, pests and diseases. And when you start to combine those together, the numbers start to get a bit frightening, because we found over 600 control measure by pest combinations which could be relevant for IPM. So, for example, disease resistance of varieties was relevant for several foliar diseases and stem-based diseases of cereals. So the task of selecting the right control methods is not particularly simple. To help with that, we created this IPM planning tool, which is free to use and available for anybody to use and look up as a source of information. And what this does is allow you to enter which particular crop types you're interested in and which particular pests, weeds and diseases you perceive as a threat that needs controlling, and it then refers effectively back to the reviews to identify possible IPM control measures for those particular pests, weeds and diseases in those particular crops. And just as an example, this is one part of one screen, in this case for foliar diseases of wheat, and it comes up with a range of possible control options. If you click on the little question mark in the circle, it comes up with a short piece of text explaining the relevance of that control method, and within that short text it also provides links through to more detailed information from independent sources on that particular control method. So it's a way of focusing down on possible control methods, and it also allows you to record which of those control methods you are already implementing or plan to implement in the future, which then acts as an IPM plan, and IPM plans can be paid for through the Sustainable Farming Incentive Scheme. So in this particular example, we can see that sowing date and variety choice are relevant control methods for septoria. And we're fortunate in that particular case that there's really nice evidence from experimental work in the field about how effective those two control methods can be when combined. And we can see here the effect of more resistant varieties such as Graham and the effect of later sowing. Now, the difficulty is that there are loads of possible control methods against loads of possible diseases in lots of different types of crops, and it just isn't physically possible to test out how all those control methods combine. But fortunately, there is a generalized rule that allows us to estimate how effective particular combinations are likely to be. And perhaps rather surprisingly, this general rule was first put forward in 1939 in the paper referred to at the bottom, The Toxicity of Poisons Applied Jointly. The poisons in this case are not related to bumping off Auntie Agatha. This is about how mixtures of pesticides and their work and how their efficacy can be predicted. And the methods described above, and this particular method is called the multiplicative survival model, and it does what it says in the tin. So if we imagine we had a particular control method, it may be chemical, it may be non-chemical, that gives 50% control of a particular pest, weed or disease, and we have a second control method B that also provides 50% control. For each of those, we can express the proportion of the pathogen population that survives treatment as a fraction of 1. So if we control half the population, then half the population, 0.5, is the survival fraction. And what the multiplicative survival model does is multiply together those survivorships. So you multiply together 0.5 by 0.5 and it gives you 0.25, which is predicting that the combination of control methods A and B should give you approximately 75% control. And this model holds true when the control methods are broadly independent in their action. So if, for example, you are mixing two chemicals within the same mode of action, then this model would not hold. But if you were, for example, combining host resistance and a fungicide, then this method should hold true. And what this method allows us to do is look, first of all, in general terms about what we might expect when we combine two or more different methods. So here's a hypothetical example. If we apply 0 control methods, we get no control, so we have a fraction of 1 of our pathogen population still surviving. If we apply 1 control method that gives 50% control, the fraction surviving is 0.5 or half. If we apply 2, as we've seen, the fraction remaining is a quarter, and so on down as we apply more control methods. And we can see the outcome of this in the chart on the right. And as you can see, it's a law of diminishing returns as you add more control methods. And in this particular example, if you wanted to achieve better than 80% control, for example, represented by the dotted line, what we can see is you would need 3 or more control methods to achieve that. So let's take a look at some more specific examples of how this works in practice. And we can think about it in these 3 examples. So we could be thinking about combining fungicides in mode of action mixtures. We could be thinking about combining particular applications in a spray program. Or we could be thinking about combining partial disease resistance genes, what's termed pyramiding, where a plant breeder will accumulate 2 or more disease resistance genes into a variety or a variety mixture. And then we can think about a more traditional form of integrated control, in this particular case integrating a disease resistant variety and a fungicide. And we have evidence on all of these and how the multiplicative survival model works. So to take a first example about mixing 2 fungicides of differing modes of action, so they're operating independently. If we express the Septoria tritici severity that we saw in this experiment in the untreated as a severity of 1, what we see is that the fungicide of mode of action A gave 41% control when applied 3 times in a spray program on its own. The fungicide of mode of action B gave 70% control. Therefore, our fractions remaining in the table on the right-hand side were 0.59 and 0.3. We multiply those surviving fractions together, and we would predict that combining fungicides A and B would give us greater than 80% control. And when we measured that in practice, we saw that we got greater than 80% control, and the surviving fraction was in fact 0.14. So our prediction was in fact pretty close. If we then extend that and think about different fungicide treatments within the same crop as independently acting control methods, we can see that we get a similar law of diminishing returns. In this example here, this is data from more than 250 crops. This is data in fact from 2006, which was a medium severity year for Septoria tritici, and we can see how of those 250 plus surveyed crops, as the number of fungicide applications increases, the severity of septoria tends to decrease, but it is again a law of diminishing returns. And we've shown independently of this in the Paveley et al. Paper, shown at the bottom there, that the multiplicative survival model actually predicts very well the effect of combining fungicide treatments into a fungicide program. Then if we move on to thinking about combining disease resistance genes in a variety, the multiplicative survival model also works well here. This graph takes a little bit of explaining, but if you imagine that you took two wheat varieties or wheat breeding lines and you crossed them, and then from that cross you produced 100 plus offspring that were true breeding, that you could then grow in the field and measure the disease severity on those offspring. And you do that for, in this case, crosses between, or 6 different crosses between different wheat varieties. What we then get is a chart like this. Along the bottom, we've clumped those true breeding offspring into those that inherited one disease resistance gene from their parents, or 2 disease resistance genes from their parents, or 3 or 4. And we can see again, as more disease resistance genes are accumulated, the level of disease control is improved, and again it's a law of diminishing returns, which again was well predicted by the model, as we show in the Grimmer et al. Paper. For an example of integrating variety resistance and fungicide, we'll take an example from potato late blight, and along the bottom axis of this chart we have the dose of fungicide applied per application, either at 7 or 10-day intervals. Those fungicides were applied to 3 different varieties: Charbonniera, which is blight resistant, Cara, which is intermediate, and King Edward, which is susceptible. And up the left-hand axis we have a measure of the severity of late blight integrated through the life of the crop. And we can see that the disease was much more severe on the susceptible King Edward and less severe on Charbonniera. And we can see that even a low intensity fungicide program on a more disease resistant variety provides more reliable control than a more intensive program on a more susceptible variety. And again, in this paper we showed that the outcome of this fitted with the model. So we obviously can't test that the model is applicable in every single case, but we've tested it very broadly and in several more examples than we've shown here, and it's generally a good predictor. So what that then allows us to do is to make some generalizations about the number of control methods that it would need in order to achieve a certain level of control. This calculation we've done to achieve 80% control, but you can choose your own value and do your own calculations using the simple equation shown earlier. What we see here is if, for example, we had a whole bunch of control methods that were all fairly ineffective and only giving us about 20% control, then we would need to combine 7 control methods in order to achieve the level of control we desire. In contrast, if we had a single control method that created 80% control on its own, clearly we only need 1. Or if we had 2 control methods that each produce 60 or 70% control, then those 2 control methods combined would be sufficiently effective. So this is making a kind of broad generalization that control methods combine in a predictable way, but the question arises about whether particular combinations of control methods might actually be more or less effective than we might expect. And you may have heard the terms synergy or antagonism used in this regard, and the definition is that two or more control methods are synergistic or antagonistic when their combined efficacy is greater than or less than expected. Now, the tricky word here is expected for two reasons. First of all, we have to have a method of calculating what we expect, and the multiplicative survival method is one of those. There are other methods, and depending on which of those methods you use, you can get different expected levels of control. The other difficulty with this is that to prove synergy or antagonism is actually a pretty big experimental task, and it's quite seldom done sufficiently rigorously. So quite often when there are claims of synergy, those claims are often not backed up by sufficient evidence. And when you actually do the work to prove whether there's synergy or antagonism, in some cases you find real statistical proof that particular combinations work particularly well or badly, but those cases are definitely in the minority, and in the majority of cases the combined efficacy of control methods is predictable by more simple means without needing to concern ourselves with whether they're exceptions from the rule. So what can we conclude from all of this? So the first thing is to identify control methods with proven efficacy. The IPM planning tool can help with that. If more control comes from one method, for example a non-chemical method, then less control is needed from another. That the combined efficacy is predictable from the efficacy of individual control methods, but each additional control method has a diminishing return in terms of its efficacy. However, a really important point, as we've seen in other videos, particularly about fungicide resistance and the management of virulence, combining control methods is really important to manage pathogen evolution and hence to maintain effective control in future. So IPM is a broad topic. The idea of holistic IPM is important, to have a broad range of control methods, but boiled right down, it comes down to picking the most effective methods and combining them. And if you want to read further on this subject, there's plenty of information online and in the literature here.